Have you ever stopped to think about how doctors can see not just what's inside your body, but what your body is actually doing in real time? Today, we're diving into the incredible technology of positron emission tomography. You've probably heard it called a PET scan. It does exactly that. It's like having a window into the secret metabolic life of our cells. So, here's our game plan. First, we'll get into what makes a PET scan so different from other scans. Then, we'll follow the wild journey of its secret ingredient, the radioactive tracer. After that, we'll see how the scanner itself turns that into a picture. We'll also look at its biggest uses, like for cancer and the brain, and wrap things up by talking about the risks versus the rewards. All right, let's jump in. Okay, first things first. What in the world is a PET scan? Because I promise you, this isn't just another medical photo, it's a whole different ballgame. Right. Think of it this way. An X-ray or CT scan is kind of like taking a picture of a building. It shows you the structure, the anatomy. But what if you wanted to know where the electricity is actually flowing or which rooms are using the most power? That's a totally different question, isn't it? Well, that's exactly the problem PET technology was designed to solve for the human body. A PET scan is all about functional imaging. It's not really focused on what things look like. Instead, it uses these special radioactive substances called radiotracers to literally watch your body's metabolism happening in real time. It's like seeing the chemical processes of life as they unfold. So, if you remember one thing, let it be this. A CT or an MRI answers the question, what does it look like? You get this beautiful, detailed map of your anatomy. A PET scan, on the other hand, answers a totally different question. What is it doing? It shows you a map of activity. And believe me, that distinction is absolutely everything. Okay, so if you want to see what the body is doing, you basically need to send in a spy, a molecular spy. And that brings us to the real star of the show, the radiotracer. So what is this radiotracer? Well, it's a clever little two-part molecule. You've got a really short-lived radioactive atom, the radioisotope, that acts like a tiny little beacon. And that beacon is attached to a molecule your body already knows how to use. Most of the time, it's a form of glucose, sugar. And this is what's so genius about it. The tracer used in over 95% of all scans is called FDG, and it's basically just radioactive sugar. So why sugar? Well, your most active cells need the most energy, and their go-to fuel is glucose. Cancer cells especially are super greedy for it. They just gobble it up way faster than normal cells. So when they chow down on this radioactive FDG, they light themselves up and give away their location. So let's follow this little spy on its mission, okay? First, it's injected, and it just hitches a ride in your bloodstream. Then it starts getting soaked up by those really active, energy-hungry cells. Now here's where the magic happens. The radioactive atom inside the FDG starts to decay, and when it does, it spits out this tiny particle, a positron. And this positron doesn't go far at all, we're talking less than a millimeter, before it slams right into its opposite, an electron. And when those two meet, poof, annihilation. They vanish, releasing this perfect little burst of energy. Okay, so that little poof, that annihilation event, is the signal the PET scanner is designed to find. But how does this giant machine capture millions of these tiny energy bursts and somehow turn them into a detailed map of your body? So, when that positron and electron annihilate each other, they turn their mass into pure energy, specifically 2 gamma-ray photons. And these photons shoot off in almost perfectly opposite directions, kind of like 2 billiard balls hit from the exact same point. That physical signature is exactly what the scanner is built to detect. The patient lies inside this big ring of detectors, and those detectors are just waiting to spot those pairs of gamma rays. The machine only counts a hit when 2 detectors on opposite sides of the ring go off at the exact same instant. It's called coincidence detection. Every single hit draws a line. And after millions and millions of these hits, a super powerful computer reconstructs all those lines into a 3D map, showing you the hotspots where that molecular spy has gathered. And this is where it gets really cool. A PET scan by itself can be a little fuzzy. You see the hotspot, but it can be tough to know exactly where it is. That's why most modern scanners are actually PET CT or PET MRI machines. The CT gives you that perfect anatomical roadmap, and the PET scan lays the functional data right on top of it. It tells you not just what's active, but precisely where it is. So now we've got these incredible, detailed maps of the body's activity. What can we actually learn from them? Well, let's look at 2 of its most powerful applications, finding cancer and understanding the brain. In oncology, PET is a total game changer. Since tumors are so hungry for glucose, they just light up like Christmas trees on an FDG PET scan. This lets doctors not only find the main tumor, but they can scan the whole body to see if the cancer has spread anywhere else. That's called staging. And maybe just as important, they can do a scan after treatment to see if the tumor's activity has gone down. It's a direct way of knowing if the therapy is actually working. The brain is another place where PET is just incredible. With something like Alzheimer's disease, for example, the parts of the brain that are affected actually start to use less glucose, so they show up as areas of decreased activity. For epilepsy, the spot that's causing seizures often shows up as a cold spot on the scan in between seizures. And for researchers, my gosh, PET lets them map out specific receptors in the brain, opening up all sorts of new avenues for understanding mental health. All right, but let's get to the reality check. The word radioactive makes anyone a little nervous, and that's totally understandable. So let's talk about the risks and actually put them into some real-world context. A typical FDG-PET scan gives a patient a radiation dose of about 14 millisieverts, or MSV. Okay, so what on earth does that number actually mean in real life? Let's put it into perspective. That 14 millisievert dose is pretty much the same amount of natural background radiation you'd get just by living in Denver, Colorado for a whole year. It's about double what you'd get from a chest CT scan, but it's hundreds of times more than a simple chest X-ray. So the takeaway here is that it's not a trivial amount of radiation, which is exactly why the benefit of the scan has to clearly outweigh the risk. And besides the radiation, there's some big practical hurdles. The scanners themselves are incredibly expensive, and so is making the tracers. A lot of these tracers decay super fast, some in just a few minutes, which means you need a special particle accelerator, a cyclotron, literally right next door. The big advantage of the isotope used in FDG, fluorine-18, is that its half-life is a relatively long 110 minutes. That's just enough time to make it at a central location and ship it out to hospitals in the area. But even with all those challenges, we keep coming back to the core value of this technology, and this quote just nails it. PET can give you information at the molecular level, way before any changes are big enough to see on a CT or MRI. It's about catching the disease process in the act, not just seeing the damage after it's done. Which really just leaves us with this one big thought. We've gone from seeing our anatomy to seeing how our bodies actually function. As this technology gets even more precise and hopefully a lot more accessible, you just have to wonder, what other invisible processes, what new secrets of our own biology are we going to be able to unlock next?